Okay, so the difference between transverse and longitudinal waves. So transverse, I don't know, maybe I'll pick a different color. Those waves are going to be pretty much like the standard waves that we've been working with throughout the unit here. You're going to have like a rest position, amplitude. So this like that area there where you'll be amplitude. Hold on. This is your trough and crest. And then I think those are pretty much the main parts. I have a couple. I could maybe ask the class. What would you call um, this distance? Does anybody know?
Wavelength?
Yep. So lambda, right? And then if say this is the where the wave starts, what would the red portion of the wave be called? So this would be frequency. Or I'm sorry, period. So the time it would take to get back, oops, to the same position on the line is the way I could think about it. So it's like a full up and a full down, right? So that's some stuff about transverse waves. Longitudinal waves. I'm sorry, by the way, that I have poor handwriting. I'll try to, and spelling. So we kind of have a compressed section, like a longer, more spread out section, then a compressed section. So you can think kind of like a slinky. I think we were supposed to do like play with slinkies in labs, but I don't know if we ever did that. Um, and then some terms like so. This would be a squish. I don't know if that's the technical term. A stretch, squish, right? That's what she calls them. But there are technical terms. So when it's a squish, so let me write it like this. In a longitudinal wave, that's called compression or condensation. And that's, I mean, if you think compress, like push together, like squish together, right? And then if it's a stretch, it's called rarefaction. So that's just in longitudinal waves. And we mostly dealt with transverse waves. We didn't really get into the longitudinal waves too much. So basically just understand that the longitudinals are like, think like slinky, and transverse are the more like wavy up and down, right? And then we can solve problems. So all the problems that we solved usually dealt with transverse waves. Um, and we used a couple different variables. So I just wanted to kind of label the variables and define them. So the first one I was kind of talking about here, let me right up here, is t equals period. And period is basically how many seconds for one wave, right? So how long it takes for, one wave to pass. And then, and so that's usually in seconds. So seconds. And if we know period, we know frequency. So frequency, oops, we say that's the inverse of period. So that's why I say if you know one, you know the other. So in this case, it's how many waves, oops, I think I go down a little bit, waves per second. So in 1 second, how many waves are coming by? And so it comes up later on, but she talks about this. T equals 1 over F, and F also equals 1 over T. So that's where she kind of gets into that triangle, right? I think it was like that, right? Yep. So you can kind of see if you're trying to find frequency, you just like cover up these parts. Trying to find frequency, you know that it's going to be 1 over T. And vice versa. If you're trying to find T, it's going to be 1 over F. So that's T and F. The other two like main ones were amplitude. So maybe I'm going to run out of room on here. Maybe I'll just go to a new sheet. So amplitude. And so basically, if we have a transverse wave, right, and it's going kind of something like this, the amplitude is the distance from the rest position, or the point like in the middle, to the top or the bottom of the wave. So this is amplitude. And there's a few ways that few things we can do to find it. I think that'll come up a little bit later on. Right now it's kind of just understanding what they all mean. Actually, no. Was there something for
Hey,
amplitude this early
Brady.
on? What's up?
Sorry, I didn't mean to interrupt you, but Kiera asked if you could add her
Oh,
in.
I'm sorry, Kira.
Sorry.
I'm sorry about that. I I didn't see you waiting in the waiting room.
That's okay.
Okay. So we're just explaining amplitude. Um, right, looking at it right now, I don't think we really had many equations that went into that. So move on for now. Mu. I think it kind of supposed to look like a little upside down H with the thing. Kind of ends up looking like an M sometimes. That equals linear density. Linear density is also equal to the mass divided by the wavelength. And so it's usually in kilograms per meter, right? Yeah. And that mu comes up in a few equations, right? So if we're trying to find the velocity of a wave, so let me just define the velocity. V equals velocity. It's
I have a
usually,
really,
what's up?
sorry,
No, no
really
worries.
dumb.
Everybody feel free
So,
to interrupt if you want.
um, on her key, like
hmm
she didn't specify that it was wavelength. She only said length. So for the linear density,
This one?
yeah. So
So,
like, is there a
okay.
difference?
Yes, there is.
Like, okay.
Let me think about this for a second. I'm wrong. I'm really sorry about that.
Okay.
It would have to be
Sorry.
the whole length of the whatever's like if it's the string, for example, and it's got waves, you'd have to have the whole length of the string. You're right,
Yeah. Yeah.
not
Okay.
just one wavelength.
Yeah.
So that's kind of tricky to think about. So mu, linear density, mass over length, so kilograms over meters. So I'm trying to think that I think that linear density comes up in those spider problems, so we'll probably go over that when we start getting to the practice or the short answer problems. But thank you for that catching that, Mary. But back to okay, velocity. Velocity for now, we can think of it as kind of like speed. I know like some physics teachers might get mad at me for saying that, but in like in this instance, we've always dealt with velocity kind of like speed. So if you think about speed, right? We usually say in a car it's like miles per hour, or you could write that like miles over an hour. But in our case for velocity, it's pretty much always going to be meters per second. So how far, or how do I phrase this? Yeah, like we could just say how far something traveled in a certain measure of time, right? So back to what I was kind of tying these two together. You can find velocity if you know the force and the linear density. So the force over, we'll say mu, right? And that kind of makes sense. Like how much force are we putting in the waves? How long is it? How heavy is it? Those would all go into how fast that wave was moving or how much velocity it had, right? A couple other useful equations. I was explaining velocity. Here's another way to explain it, right? When I was saying it's kind of like speed or miles per hour, you can find velocity if you have a distance and a time, right? So if you're going 12 meters per second, that means in 1 second, so you're going to travel 12 meters. Does that make sense to everyone? Like I said, if there's any questions. Oh, man. Hi, Emily. I'm sorry. I hope you weren't waiting too long. So, okay. Let's kind of go check back on the study guide. We covered pretty much, I think that was all of them, right? We covered, oh, I'm sorry, energy. Let's go back and check energy. So there's two equations. They didn't come up too much in the homework, but they're still useful to know for sure. They might come up on the test. So if she asks, like, how much energy does a wave have? Or what's the wave energy? There's an equation, and these ones are on, I'm looking on page 23 in her notes, and they're at the top of the page. So it's going to be E over L equals 2 times pi squared times the frequency squared times the amplitude squared times mu. And that will ultimately give you joules per meter. I should make that a little m. Right? So it's kind of like different from velocity, right? Where instead of like how far per a distance or the length, how much energy is going to be in that length of rope, right? So actually, forget about the velocity thing. I don't want to confuse you. So energy per how much length we have, right? If we're trying to find power, power is a little different. So wave power. It's very similar. They're almost the same equation. So P equals 2 times pi squared times frequency squared times amplitude times mu times velocity. Right? The only difference is, I mean, maybe some of our, more electrically inclined people could explain better than I can. But this is, from what I understand, joules are always like a unit of power or energy. Energy, we'll say, unit of energy. So the power that the wave has is different. It's not over length. It's just going to be joules per second. So this time, it's kind of like how much power is it putting out in a unit of time, or how much energy, I should say. This could also be, this is the same thing as watts, or just a W. Does that sound right, Jeremiah? It's okay. Like I said, there wasn't too many homework problems on this stuff, and as long as you know, like, kind of what all the variables mean, right? You should be able, and she asked you about wave energy. You should be able to plug those all in, right? It's just a matter of putting things into your calculator, which might be tricky. So if anybody has problems with that kind of stuff too, maybe we can, meet a little bit one-on-one toward the end, and I can help, try and help. Okay. So, let's see. We covered the difference between transverse and longitudinal. So the transverse are like the kind of curvy ones, and the longitudinals are the slinkies. We kind of went over solving problems. We just did a brief thing. Maybe later on we're going to show some more examples of actually solving a problem. Because I just kind of want to do a brief overview of everything and then dig deeper from there. So model relationships between wave properties and characteristics. So that kind of has to do with that first lab that we did. Would be a good example where she asks, the main point of the lab, right, was to figure out, let me just double check, like what the difference, or how would the amplitude of a wave be affected by the force of the wave. That was the kind of main thing we were looking at. And then we could tell from the lab that the force didn't necessarily have a huge effect on the amplitude at the in our experiment, just because the it was loose, right? There wasn't a lot of force. But if there is a ton of force, there hits a point. It's like on an X, like a log curve. So if there's a ton of force, then the amplitude will start going down, right? And that makes sense because the harder we pull down the string, the less number of like nodes we would have, right? So the harder you pull, the lower the amplitude would be, right? Because this string wouldn't be able to go up and down as much. So that's one relationship. There's a lot we could talk about. I think one of the short answer questions. Here, I'm unprepared. Yeah, it says graph position versus time. So just That's an example of just showing the relationship between the position of a wave over time. You could talk about, there could be all kinds of different questions, like, say, what happens to the period if the frequency goes up, right? If we had, say, the frequency was 6, we'll write hertz. You gotta always remember your units. That means the period is the inverse of that, right? So it'd be 1 over 6 seconds, right? So just seeing that relationship as the frequency goes up, so say we're at 10 hertz, the period is ultimately going to go down, right? Because 1 over 10 is a smaller fraction than 1 over 6. And that makes sense, right? Because the period is how long it takes for, or, sorry, let's go back up so I can, period is, yeah, how long it takes for one wave to go by. So how many seconds per wave. And frequency is how many waves happen in 1 second. So if there's more waves happening in 1 second, that would mean the period of time for a wave to go by would have to go down, right? So those are just a couple of the relationships. Okay, so now let's move on to week 3. We're getting into oscillations, so springs and pendulums.
Oh, until we moved, can I ask a question?
Yeah, sure.
So if she will ask something like how frequency connected to amplitude or like how period connected to amplitude, should we use a wave power equation to find this? Can she ask something like that?
You could totally. Yeah, so if you're given values, right? Two different values of amplitude, you could use and say, what were you trying to find? Wavelength, did you say?
I mean, for example, like how frequency connected to amplitude.
Frequency and amplitude.
Mm-hmm.
So the frequency isn't necessarily really affected by the amplitude at all. Because the amplitude is just like how high up and down the wave goes from the rest position, right? So if the wave's coming in faster, it doesn't necessarily affect the amplitude of the wave, right? Theoretically. The only thing, if we kind of look at some of our equations, seems like amplitude can be affected by pretty much mostly the force, right? I mean, also we didn't really have it in the beginning here, any equations that had to do with solving for amplitude, did we? But that was more in like when it came to the light optics stuff, right? Let me just try and explain it, I guess. So, if the frequency, right, what does that mean? The wave is coming in at a faster interval of time, right? If nothing else is affected besides the frequency, I don't think the amplitude would be affected. Does that make sense?
Yeah, thank you.
Mm-hmm. Do other people agree with me on that?
Hey Brady, I have another question.
Sure.
Okay, so position, what is that? I guess is that the frequency?
So we'll get to that. That's coming up in this oscillation part. So I can go to
Okay,
that right away. So
I was just wondering because
position.
it's not our short answer
Yeah.
question.
Yep.
Okay, thank you.
So the best way I can explain this, the way that it made the most sense to me was when the example with the pea in the bowl, right? So its position is just where it is on the wave, right? So right here, you could call this X, like its position. If the ball was over here, this would be its position. So it's just kind of another term, I think, the divergence, right? It's just basically where it is a good way to think about it. Does that make sense?
Yeah, that does.
Yeah. Okay. So that's where we'd get questions like, um, what's its velocity at this position? Or, at what time would it reach this position? Right? And that kind of makes sense because if you think about the P, you can actually visualize something that's actually going back and forth, right? And then you can think at a certain interval of time or at a certain period, you could find where that P is going to be in the bowl, right? So let me check. Hold on. So what does she have on the study guide? Let's see. So apply concepts of superposition and oscillation. Right. So define simple harmonic motion and give examples. So in our notes, we're kind of on page 34, 35, and oh wow, it goes all the way to like 41. So week 3 stuff. So simple harmonic motion is just like your simple pendulums and springs. She doesn't really have it defined anywhere, does she? I just want to know like the textbook definition of it.
She doesn't.
No. Well, I could try and explain superposition. So superposition is when like two waves or more are like in the same space, right? And they like displace each other. So okay, she does have some stuff here. So when she was talking about the noise canceling earphones and stuff like that, that'd be an example of like destructive interference. Constructive is when it made it grow, right? So those are both examples of like a superposition. So here's the actual textbook. Principle of superposition. When two or more waves are simultaneously present at a single point in space, the displacement of the medium is the sum of the displacements due to each individual wave. And we kind of got more into that displacements when we started talking about like the light optics and the fringes and the lights will kind of do destructive interference and constructive interference in different zones. Sound will do the same thing. So that's where she gets into that like 2 point, where if you're at a concert, there are regions where it's louder and the sound quality would be higher, and then there's regions where it's quieter, and that's because of destructive interference, right? And constructive. So the places where it's higher are the constructive, places where it's lower are destructive. And if I could tie that in to the next question or the next section, when we deal with those, those light with the screen slits and you're trying to look at the interference patterns, the dark spots are the points where it was destructive interference, and the brighter spots are the points where it was constructive interference. So that's kind of superposition, and I think harmonic motion must just be like pendulums and springs, just going back and forth in a way that we can easily like measure and see, right?
Can I add on to that?
Mm-hmm.
So like basically your simple harmonic, so like your pendulum, for example, is a really simple example of it. But on one side, that's your the highest of potential energy with um the height of that is at to its max, but in the middle, that is your highest kinetic energy. and highest velocity is the max, but there's zero height to it. So, and then when it hits the other side, it's basically the same thing as well. But between kinetic and between potential, it's split 50-50. If that makes sense. Yeah. Brady, are you talking?
Yes, I'm sorry. Thank you.
Were you on mute?
Yeah, I'm muted. Well, I muted my microphone.
Oh, okay.
That's my bad. Okay.
Okay.
So kind of what Mary was saying. When this is a pea bowl, right? When you're at the top of your pea bowl, like, or even you could think about this like a kid back and forth on the swing when you're a kid, right? When you're at the top of your wave, right? Your peak on your swing, you come to a stop, right? So that means you have 100% of your energy is converting into potential energy, meaning it has the capacity to do work, right? But then, as gravity starts to pull the ball and it starts moving down this way, it's gonna cross this rest position, right? So we call this, oops, rest position. It's gonna convert all the way to 100% kinetic energy, because that's the point where the ball will be traveling the fastest or have the highest velocity, right? And then as it comes up this way, it's going to start losing that kinetic energy the higher up the bowl it goes. And once it gets to the top of its peak or whatever, or top of its amplitude, it's going to convert all the way back to 100% potential energy. And this cycle repeats itself. So as the ball comes back down, it all gets converted to kinetic, goes back up, potential, back down, kinetic, right? So something useful to know at rest position, energy is 100% kinetic, right? Does that kind of make sense? So potential is like a cup hanging off the side of the table. It's just ready to go, right? And if somebody came and blew it over, it would start and it would all turn into kinetic energy, right? And as that cup of milk's falling, it's at kinetic energy, and then once it stops, it's potential again. And hopefully that kind of makes sense. I like to think of a kid on a swing or the pea bowl is the best way for me to kind of think about that example. So hopefully that kind of clears up what Mary said, or just kind of builds off that if you guys didn't understand. Let's see then. We need to do set a guide. So yeah, we kind of went over some simple harmonic motion, give some examples. Let's apply some equations involving variables and oscillating motion. It's everybody's favorite part. So this is where we get into those equations in like that red box. And there's a couple other ones that are useful to know. Like the force in a spring one might come up. That one was a tricky problem on the homework. But mostly, those ones in the red box are the ones that I think I used the most, and the ones that were the most important. So we can kind of go over some of those. I know some people struggle kind of with the position one, so maybe we could talk about that. There was a homework problem that was like kind of, they gave you, like, it was in the form of this equation. You had to figure out stuff from it. Ft. So this is an example of one of the equations that you need to know how to use. So in this case, x just means position. We kind of went over that. A still means amplitude. What's up?
Sorry, my bad.
No, you're okay. And this means frequency still. And time. So really knowing like what each variable means in each instance is kind of important. So maybe I could touch on now. I know me and a few other people were talking about M. M's a rough one. There's quite a few different things that it kind of seems to mean, right? So for this, the first two kind of sections, it equals mass for the most part. Right? Yeah. I don't think anything in section 1. I think in section 1 it just was mass. Kind of move ahead to the next section. M is the fringe number. And then it could also mean the magnification in our last section. And I think that was it. Was there another M?
Antinode.
So that was the, I knew, okay. My brain was like, there's another M. But it also means mass too.
Wait, because you put the fringe number, was that the
Mhm.
unit on oscillations where she put M equals the nodes or pods that she called them?
Yes. So that's what kind
Or
of,
is it different?
that's what Mary's saying. So antinodes, right? So if we have one transverse wave, and you have like kind of another thing like this, each pod you can count as like one antinode. So where in the notes is that again? I just need like a refresher on that stuff. Do we know?
In her video
It's on page-
lecture, oh, page 40, you said?
Yeah, page 40, she's got in there M equals pods. Well, I put pods, but it was supposed to be antinodes.
Was this in,
Yes.
because I remember, it wasn't in her lecture video, I don't think, but she did write it down in class.
This
Okay.
one? That's what you're talking about? Or F equals mv over 2L? So that kind of has to do with more when we're talking about the superposition and having two waves, right? And an incident wave, a reflected wave. So an incident wave is like the actual wave created at the source, and the reflected wave is it says energy reflected off an obstacle in a medium, so the opposite incident. So then what I
Brady,
don't really, yes.
can you let Jeremiah back in?
Oh, sorry. I'm sorry, Jeremiah. How long were you gone for? That's my bad.
No,
Can you
that's
hear
all
me?
right. I was just trying to reset it. I couldn't see what you were writing.
Okay. Is it working now? Can you see?
Yep. Totally
Yes.
can see it.
Okay. So yeah, M can also mean the number of antinodes, which we call pods. A lot easier to think of, right? Like when you see a circle, that's one pod, two pods, three pods. So mass we know. The fringe number, I'll explain about that a little bit more because I think somebody was asking a question. If we have kind of like this light thing like we had, so we got a central maxima, and then a couple more lights, right? Our M values, so this would be M equals 0, and then this would be 1, 1, 2, 2. So for starting from the central maxima, or the center beam of light on the screen, I guess this is more like light optics, so the next section. But just to explain it, because we're talking about M, it's just the number away from the central maxima. So if we're talking about, this one, M equals 2, right? This is M equals 1, this is also M equals 1, and M equals 2. There's no negatives or anything like that. They're both just positive, kind of working from either side of that central value. I think that's it for M, right? So then if we talk about magnification, maybe we'll get into more of that kind of stuff when we get into like the ray diagrams and ray optics. But yeah, M is a tricky one, so just try your best. Look at it's going to go in order, right? She said. So in the beginning, M is mostly going to be mass, and then we're going to move on to the antinodes, and then the fringe, and then the magnification. So if you kind of think about it that way, we're going in order. So your M values will also kind of be corresponding to what we're working on. And just kind of, I think being able to recognize, like, okay, I remember waves. That was in the week 2, like the first section. I can go to that part. Or if you start getting into, it's asking about, magnification, that's the ray optics part. There is I think it's 35 she gave us for the long problems that asks about giving some info, what are the angles for M1 and M2? And there was an equation that was given kind of on the board when we were working on the homework. And I don't think it was in our notes. So I kind of want to just talk to people about that. It is, go in red, sine of theta equals M. In this case, this is this M, wavelength over distance. So I would assume this is the equation that we're going to need to solve that number 5. Because that way, if we're given a wavelength, and a distance, and it says, given some info, what are the angles of M equals 1 and M equals 2? We'll probably be given this information, and so we'll be asked to find the sine of theta equals, we'll do M1 first, so 1 times 3, right, because 3 was our wavelength, over 6, right? So I'll kind of explain how to do this. I know some people kind of struggled with plugging it into their calculator. So the sine of theta equals 1/2, or see, I get 3 over 6 equals 1 over 2, right? So how you would plug this into your calculator is you'd have to do sine inverse. So usually you hit that like second button and you hit sine and it should give you the inverse. And then we're going to times by 1 over 2, and that'll equal theta. or whatever values you get for wavelength and distance. Right? Does that make sense to everybody? You know how to do the inverse? Yes, no? You guys see the button I'm talking about?
And then you said that just for inverse of sine, only to get angles.
Yeah, basically, because with sine is always going to be attached an angle for the most part, and it's either going to be in radians or degrees. And I think we deal with degrees for the most part.
Okay,
Um,
I was just sure.
mm-hmm. Oh no.
What problem is this page on?
This has to do with like 47, right?
Okay.
And it comes from like this equation is a simplified version of some of the ones that she gave us and talked about. And it has to do with some trig functions, stuff with triangles, right?
She
Okay.
said this is going to be a short answer, right?
This is, yep. This would
Okay.
be the fifth one that she went over.
I had a question on like the first one with the spider.
Yeah.
So we had the one in the problem and we found the time it took for the one spider. Would we just do that twice and see which one has the slower time? To find which one's the fastest?
Yeah. Yeah,
Okay.
I think that'd be a good assumption. Right?
Okay,
It's going to be a
thanks.
similar problem where it's wondering how long would it take. Oop. Megan's trying to join. Let her in. Hi, Megan. I'm sorry you weren't for not letting you in. I hope you weren't waiting too long. What were we just talking about? I'm sorry. We're talking
The spider one.
spider.
Spider.
So that was we did a problem just like that. It was at the end of the first week there, right? And I think you know what I'm talking about. So we just had to use mu to find the velocity, and then we knew the distance it was away, so we were able to figure out how long. So then, yes, you would be right. You'd figure out how fast one spider would be able to figure out that a bug landed on its web, how fast the other one did, and then which spider will know they have lunch first is the one who can see the waves or feel the waves, I guess, the fastest or in the least amount of time. So
Okay, thanks.
yeah, no problem. And then we kind of talked about graph position versus time. So when we're doing graphing, the first thing, so 1 versus 2, right? And then we're doing a graph. This is always your x-axis. This is your y. So the first thing said is going to be on the x-axis. Here, I'll do it like. The first one here is the x-axis, and the second one is the y. So it said graph position versus time. It would be, oops. I'm right about that, right? The first one's x, second one's y.
She told me that the first one is the y and the second one is the x
Is that right?
whenever listed. So it would be yeah, that's what she told me when we were graphing one of our labs.
Just like this. See, I always thought it was the opposite of that. Like in math,
I
it'd
always
be
thought
like.
that time went on the x-axis.
See,
Yeah,
that's
because
why.
time is the independent and position's dependent.
Yes. See, that's where I thought though too, Jeremiah. And then when I was listening to what I was saying, I was like, wait, time is usually on the bottom.
Because x is first, it goes x, y, so that makes sense. But
Yeah, and that's what I'm thinking. Usually, like in the past in chemistry, if they said graph something versus something, usually the x-axis is the first thing that's said. But you're right about time. Time is usually on the x-axis. So I think I would go like this. If you're choosing to do that problem, have time on the bottom, position on the side. I agree with you guys. I don't know if that's like a set rule. Um, I just kind of want to look it up quick. Just to me, you say X first. Like, that's just a math thing. You always say X first. Maybe someone could ask Shannon. Well, I don't know. She's gonna give that away, right? Let's just um, if you just Google a position versus time graph, all of them look like time is on the bottom for the most part. Yeah. So that's a safe bet. Time on the bottom, position on the side. Okay. So let me kind of get back to the study guide. Cool. So maybe some more equations involving variables of oscillating motion. We could talk about kind of the two big ones for springs and pendulums, right? So you have your simple pendulum equation. I can't find it right now, but I think I know it. 2 pi times the square root of length over gravity. That's your simple pendulum. That's going to be really useful. Know that gravity is always 9.81 meters per second, or you could write that as squared. But there were problems where G was different. Remember, there was a question on the homework where it was like at the equator and at the North Pole, they have two different gravities. So this 9.81 is really just an average of like the whole globes. Because it's like the farther away you are from the surface of the Earth, the less force that gravity would be pulling down on you as. So if you're, say, on the top of a mountain, it's going to be, you know, a little bit less than this. Where if you're closer to the equator, it might even be a little bit higher than that, if that makes sense. But 9.81 is definitely something that you're going to have to need to know and write down, if it isn't already. Because that'll come up. And then the other one, so T equals 2 pi times let me see if I can find this one sec. Here it is. It's mass, yes. Mass over K. Right? And so this is for simple springs. And this K value is another variable that I didn't really talk about yet. This is your spring constant. Right? And it has to be like determined, like it isn't a set value like the way gravity is. Right? So there might be problems where they ask about, you know, what's the spring constant if it has a certain period in mass, right? So this would be the equation to use. So ultimately, like I said, there's kind of a process for solving these kind of problems. The way I like to think about it is first you write what you know. So what do we know? And I like to write that just easy for me to see. So whatever's given in the problem, if I'm given a mass, if I'm given a frequency or time period, amplitude, any of those things, I'm going to write it down right away. And then I look for what do we need to find? Like what's it asking for, right? So is it asking me to find the spring constant? Is it asking me to find period? What is it? What do I need to figure out, right? And then once you know those two things, you can kind of determine what algorithm am I going to use. And that'll be a little bit easier once you know, okay, well I have the period and the mass, say, and it's asking me to find the spring constant, and you go look at your red box, or even I would tell people to get used to that kind of cheat sheet that she gave us for waves and optics. Really useful. It has all that kind of stuff on it in one place. So if you get used to that and knowing where everything is on there, there's less searching involved then for different equations. But yeah, for this, going back to what I was saying, you know, if we're given period and mass, we're asked to find spring constant, we'd look at that, our equations, and be like, okay, for a mass spring system, there's an equation here that looks like this that I could use and plug in these values and find K. Right? So then I guess a kind of a fourth step, it's kind of optional, depends, you know, how brushed up your algebra is. But what I like to do sometimes is rearrange to solve for what we want. So if I'm kind of sticking to this example, we're looking for K. So T equals 2 pi times the square root of m over K. We can do some math tricks to get K by itself on one side instead of T. So what I would do is I would divide by 2 pi. So you get T over 2 pi equals the square root of m over K. Then you square both sides. So you end up getting T over 2 pi squared equals m over K. And then, so what you end up doing is multiplying by K and then dividing back out this stuff. So K, so skipping a couple steps, I guess. K equals m divided by T over 2 pi squared. So now I have an algorithm that's kind of like formatted in a way where I could just plug in all my values, put it in my calculator, and I'll get K without having to do too much extra thinking. If you're good with your algebra and you can flip stuff around, you can do that. Otherwise, you know, what I would do too is you can just plug in all your values first and then do that during. But it's kind of easier for me to do it with just the letters before putting in the numbers in personally. I found that it's easier to get kind of mixed up or put some wrong answers in if you're trying to do it all at once in your calculator, right? So that's kind of talking about applying equations involving variables in oscillating motion. And so now we're talking about those. We already kind of covered the interference and the superposition waves, I think, pretty good. If we wanted to diagram that, a good way to diagram that would be, you could even, we're allowed the whole binder, so you could just kind of look, right? So that's when we'd be, you could just look at those two diagrams. They are right on page 38. Underneath where it says constructive interference, there's a diagram for it. And underneath destructive interference, there's a diagram for that as well. And some diagrams for the 2 points patterns. Right? So it's kind of like this idea that we have one wave and we have another wave. And they're hitting at just the right frequency to where they're actually making the overall sound louder or bigger. It's called like they're growing or resonating, right? So if two frequencies resonate, they kind of grow on each other and it makes an overall bigger sound. Kind of like how chords in music works, right? Like, I don't know if anybody's musically inclined, but if you know, like a C chord is a C, D, and a G. You know, the C is your main one, but the G and the D frequencies kind of make that C resonate louder. And then you can have the opposite, so you can have destructive interference. So you have, you know, one wave is like a sine wave, and one's like a cosine wave, kind of. So they cancel each other out, and that's how your noise canceling headphones work. Oh shoot. Oh yeah, that's right. because ultimately these all cancel each other out and you're going to end up with just no sound. Kind of cool stuff. So that would be just kind of diagrams. Obviously, those were really not very good, so you'd probably want to make them better than that. But I hope you kind of get the idea. So superposition is just when there's two or more waves that are present in a single space. And we could say interference is just like, it can be constructive or deconstructive, right? So now let's relate concepts of standing waves to the production of sound. So this is where we'll kind of get into how the human ear works. Maybe I'll touch on some of that stuff in case it's on the test, and we'll get into kind of how sound waves work a little bit more. So kind of backtracking a little bit. Human ear. I mean, this is a chemistry exam. I can't see her really testing us on the anatomy of the human ear, but on the outside, this is the flap. I guess this is kind of a crappy little ear, but this is the flap. And then you got your canal. And so the flap is kind of like an antenna, right? It collects the sound waves, directs them into the canal, where you have an eardrum. Eardrum vibrates, right? Because sound waves go pass through it, and the kind of vibrates back and forth as the wave passes through, and that then causes the hammer, right? And it's called that because it kind of looks like one, something like that. So the vibration of the eardrum causes the hammer to move, which then hits the anvil, right? So I don't know how to draw that, maybe like this. And then that hits the stirrup, right? So we'll call this anvil. 3 smallest bones in the human body, and they're called the ocelles. So ocelles bones. So the ocelles bones isn't like one singular bone, it's all these 3 together. Hopefully that makes sense. And then you have your semicircular canal. I mean, that's just more for balance, has less to do with hearing, so we're not really too worried about that. But the next main part is the cloaca. Kind of looks something like that. And this is where all those vibrations get transferred. And then in the side of the cloaca, there's like these little cilia, or kind of like hair-like, I don't know, things. And as they wave back and forth, there's nerves connected to them, and they're auditory nerves. And so the vibrations get picked up as sound, and our brain hears them as sound. Kind of cool. Oh, I didn't label this eardrum. And then some other things to kind of talk about. The speed of sound, the main value that we're going to want to know is at 20 degrees Celsius, which is about room temperature. It's going to be 343 meters per second. And that's going to be our main value to know for probably a couple of equations. There were definitely some in the homework where we kind of had to know that, and it wasn't given in the problem. And then I think that was mainly it, though. I guess water too, maybe. Water would be good to know. Water is 1480 meters per second, right? So why is water so much faster than air. It's because in air, the molecules are spread a lot farther out than they are in water. So if there's a wave coming through here, waves need a medium. Or in other words, they need something to go through. Like you can't swim if there's no water, right? So if you were in space and you got tossed out of a spaceship and you're screaming, nobody's gonna hear. There's no sound. There's no way that any sound can travel in a vacuum. You need a medium. In air, the particles are spread out a lot more than they are in water. So that means it takes longer for this particle to feel the wave and then hit into this particle and then hit into the next one and so on than it does for the water. Water is going to be a lot easier for it to go bang, 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 bang. Or if you had something like a diamond, diamonds are going to be like, you know, super dense, super tight. So this wave is going to be able to go travel through all these particles really fast. And you can see that. I think the speed of sound in diamond is like 14,000, right? No, 12. Sorry. 12,000 meters per second, which is really fast, right? There was kind of a homework problem where I know it sounds counterintuitive, but in colder air, it tended to go slower than did in faster air. And you would think cold, right? The more closer the molecules would be. Hot, the wider spread out. So I guess it makes sense. Colder it is, the closer they are. You think it would be faster, right? It's not. In air, with higher temperatures, come faster speed of sound. And it's just it has to do with the energy in the particles. And if there's more energy, they can kind of bang into each other faster. But this is up to a certain point. If it gets really, really hot, the particles are spread out too far and they can never reach each other to have that wave pass through, right? So I'm not trying to confuse you. Basically what I'm trying to say is less dense equals slower, while more dense equals faster. I think that's the main concept that to really understand when it comes to like the speed of sound. And then we could kind of go over intensity and stuff like that. It's just it's not loudness. It's kind of like loudness. Loudness is subjective, like she says, so it's just how much power over a certain area, right? So how, I guess, loud, right? Or how intense that sound is going to be. And then, so I think that covers that. Let's go back. Oops, it changes. So we related the concepts of standing waves to the direction of sound. Not really. Let's try to do that. So standing waves, I think there's a kind of a synonym for transverse waves. So this. And this also how sound waves are represented, right? If you're looking at them from the side, if you're looking at it like a top-down view, like say this is like some kind of like blowhorn or something, right? The sound's really gonna travel out, like this, like a ripple in the pond. But each of these, this is gonna be like a peak, this is gonna be a dip, peak, right? So if you're looking at it, you know, from the side, that's what you would see is the ripples. But sound travels out like in all directions from the source, if that makes sense. Is that necessarily true? guess not. Like if a person's talking, it'll still radiate out. Like so it'll go like this, right? And eventually it might get back around to like toward behind it. But it's not just like dude starts talking and a wave comes out just in a straight line, right? It's kind of like here, I'll make it more clear. It's kind of like this kind of thing, right? But you guys can see how waves or sound travels in like transverse waves, kind of, right? Make sense to everybody? And that's where we kind of get into the Doppler effect. So say this was a car driving by. Oh no, that was terrible. We'll just go like this, right? This is a car. And it's blaring its horn. It's got a siren, right? As it's driving by, the waves in front of it are going to be really tight together. But as it gets further behind, the farther the waves will spread out, right? This is known as the Doppler effect. And so it's kind of like that, as a race car comes by, it's kind of like a high pitched, like a vroom, and then it goes down, right? It goes lower and a little bit slower, kind of more spread out. And that just has to do with, if there's a higher frequency, so higher frequency equals higher pitch, and lower frequency equals lower pitch. Right? And it's so kind of like it's the waves are coming from a source and they're being pushed along, so they kind of condense on one end and spread out on the other. And this also causes color shifting too, because light is also can be considered kind of like a wave, right? Like Einstein copped out and said it was particles and waves. Some people argue that it's particles, right? But light definitely travels in different kind of ways. Like we can see that with color, right? So the visible spectrum. So I think red is on the lower end at like 400, and the violets are like in like the 700s, right? So as it's going away, you like say, you're looking at planets, right? This is how they figure this out. They're looking at a planet that's moving away from them. It's going to kind of have a red hint, right? Because those are the longer, more drawn out, less like slower frequency waves. Where if it's coming towards them, it's going to have like a bluer shift, like a purpler shift, because that's the shorter, higher frequency waves. I'm pretty sure I'm right in that. I don't know where in the notes that is. I know it's in there somewhere. But I'm almost positive. Yeah, red has the longest and blue is the shortest. And the guy who figured that out is Hubble. And he made a bunch of telescopes. Or a telescope. My bad. Okay. So we covered now kind of the first two. So we got two more. We started getting into the kind of optics. Right? So light optics and ray optics. The first thing it says here, discuss the applications of different regions of the electromagnetic spectrum. So, the electromagnetic spectrum, this is kind of what I was talking about with the light earlier, similar. There's different kinds of waves, right? There's radio waves, microwaves, infrared waves, ultraviolet, X-ray, gamma rays. We've heard about all these. And there's a kind of a chart on page 44 that compares them all and shows the difference. So like radio waves are on the left end of the electromagnetic spectrum, while gamma rays are on the far right. And so gamma rays are really short with a high frequency, while radio waves are longer with a lower frequency. And they kind of get more damaging to us as they go up. Mammals, right? Our visible spectrum's kind of right in between. I think it's around like 500 nanometers. Yeah, it's about the and I was right. So I was wrong. 700 is the red, 400 is the purple. Which makes sense. Because you'd want a shorter nanometer value to have a higher frequency and a lower to have a long. Does that make sense to everybody? So like, if it has a long, you can see bunch of space in between each like crest and trough. That means it's kind of like a longer wave, right? Or it's got a lower frequency. Where if they're all scrunched up and like really close together, that means it has a really high frequency and it's going to be a lower wavelength, right? So that kind of gets back into the relationship between like frequency, wavelength, period, things like that. So that's kind of has to do with electromagnetic spectrum. There are different applications. So we can talk about, I guess visible light. Really good app. There's an application for visible light is obvious. We can see, right? Ultraviolet is kind of what people talk about when we get from the sun, right? Helps us get tan. X-rays are really nice because they can go through human tissue, but it can't bounce off or can't go through bones, so they reflect back, and that's how we get X-rays. Radio waves used for communication. Microwaves we utilize for the heat that they can produce, right? Like there is a lot of applications for all these different types of waves in the electromagnetic spectrum. Jeez. I think that's what she means by that. Discuss applications of different regions. So yeah, we kind of went over that. Like I said, page 44, if you wanted to look, and then it also kind of shows an example of a light wave, or particle, whatever you want to call it. No. Differentiate between opaque, translucent, and transparent. So opaque. Does anybody know what opaque means? Sometimes I feel like I'm just talking to myself. Is anybody here?
No transmittance.
Yeah, so opaque just means like you can't see through it. Like your hand is opaque. You can't see through your hand, right? That's the way I think about it. Like opaque, I don't know if there's some trick to that. Just opaque is not clear. Like it's like solid. Like anything that light does not travel through, right? So I see where you see no transmittance. Translucent is kind of we'll go to that one last. Transparent. So if opaque means light can't get through, what do you think transparent means?
That it can get through.
Exactly, right? And so translucent is kind of somewhere in the middle. Like some light can get through, some is getting blocked or reflected back. If it's completely transparent, it's like a window. So opaque, I guess you could say like wall. Transparent's like a window. Translucent's like a stained glass window maybe, or even like a dirty window, I guess you could think of. Like something that's like partially clear, but not all the way. And so she used the term transmittance, and so did Jeremiah there. And I think that just basically means if you kind of think of the word what transmit is like kind of pass from person to person or one side to the other. So you can kind of think of like a barrier, and if it's opaque, nothing's getting through that. Where if it's translucent, some is going to get transmitted, but some is getting returned back to sender. And transparent, it's all going through, right? And then a couple other terms I guess we could go over are the reflect. So reflecting just means bouncing straight back or bouncing at the same angle that it hits an object at, right? Just like mirrors reflect. Where scattering is kind of bouncing just anywhere randomly. And then, like I said, transmitting, it has to do with passing through. By absorption, scattering, natural phenomena. So can we think of anything that would like scatter light in nature? I think me and Jeremiah were talking about this the other day, kind of. When do you remember that, Jeremiah? We were talking about how sometimes you can see like a beam of light coming through like a cloud, and that has to do with the water particles in a cloud scattering the light.
Yeah, like particle density.
Mm-hmm.
You have a lot of crap in there, you can just see the light.
Exactly, yeah. Or if you're on a sunny day, if it's being scattered off your window or something outside, you can see that beam of light coming in, right? But it's not perfectly reflecting off anything. It just seems like it's kind of random. But yeah, that'd be an example I could think of is when light scatters, in a cloud and you can see those beams coming through.
So like,
Yep.
sorry.
No,
So
no.
like a sun catcher, like on the window, it's scattering that then, or like, am I think like kind of like that? Am I thinking too hard?
No, that makes sense. Or think about like, you know, a really shiny diamond or something, right? Where they kind of, I guess no, because that would be reflecting light, wouldn't it?
Right.
Scattering would have
But
to
yeah,
be.
no, I get like with nature and the cloud or the like the fog or smoke that she
Mm-hmm.
had
Yeah,
on the
because that
like
was another question
clouds.
that she asked, right? Like, can you see light rays on like a bright sunny day with not a cloud in the sky?
Yeah.
No, you can't, right? Like, it's
Well,
just
yeah.
you can't like see the rays. You would need something to either reflect or scatter that light in order to see the rays actually. Does that make sense?
Yeah.
And the difference between reflecting and scattering is just scattering is random while reflecting is like measurable. You can predict how it's going to reflect, where scattering is unpredictable. So I'm trying to think absorption. Does she talk about absorption or am I missing something? Like absorbing is just like taking in the light, right? So like if something's black, black absorbs all light, right? While white reflects all light. Have you guys heard that before? Or if you wear a black shirt on a sunny day, you're gonna get hotter than if you wore a white shirt on a sunny day.
I think what she was talking about was the surface texture. Remember where we drew paper, but it was jaggedy, and then we drew a mirror and it was flat. So
Yeah,
one
for the
sort of,
scattering and reflecting.
yeah.
So, do you have any ideas what she means about absorption?
So I thought that had to do with the absorption when we drew the paper and it was jaggedy because it wouldn't reflect the light back.
Mm-hmm.
Maybe
Some was
maybe that's one.
absorbed. into the grooves or something?
Googling it, and it's pretty accurate with what Jeremiah said.
Really?
Yeah.
Maybe.
Absorption of light? What'd you Google? Absorbance of light.
Yeah. Let me see.
So it just says,
Like it doesn't reflect, so it just absorbs the light.
mm-hmm.
Um, let me
And you
No,
see
I
the stuff
think.
where I was kind of talking about? Where,
Yeah, I do. I think I was actually wrong because over what I was talking about, it literally says reflection. So I think you're right.
looking at scattering and reflecting? That would make sense to me, too. If it's perfectly smooth, it would reflect, right? Where if it was like microscopically really jagged and messed up, that's gonna cause like random reflection, right? That makes sense. So when I'm so absorption, did she say that anywhere in the notes? Does anybody?
see anything in the notes at all.
Me either. I could kind of
I
just.
don't
She
see
does
any.
list five. She does
What's
list
that?
5 assumptions of light rays, and she puts in there travel forever unless interact with matter, and then she's got A, reflecting, refracting, scattering, and absorbing. So I'm assuming it has to do something with week 5 because scattering is also in there.
Okay. She has it on week 4, which is what I'm confused about. Like, on this cheat sheet here. But it's all good. I think I understand absorption. Like, it's just like there's different waves that absorb light, or different, like, have you heard before, the color that something appears isn't actually the color that it is, it's the color that it's reflecting, because it's absorbing all the other light waves, right? So if something's green, it absorbs all the other light waves, so the red is orange, yellow, blue and purples, and then it reflects the green, and that's why you see it as the color green. Does that make sense? And then white reflects all light because it is all the colors. Like, so if you took a beam of white light and put it in one of those prisms, it kind of comes out as a rainbow and splits up because every color is contained in white, where black is kind of the opposite. It absorbs all light. I hope that's what she means. I'm not sure who spoke up about where they saw absorption. Can they say what page that they saw the absorption? Was that Kira? No?
She doesn't explain absorption, but she uses the word in one of her assumptions of light ray after number 3A.
What page?
57.
50. Okay.
Same for scattering. It's right at the bottom of the page. She gives a definition of it.
Oh, I see. So she just talks about. So yeah, it's pretty much kind of what I was saying. And I don't think we're going to be tested too much on it, so we shouldn't focus too much on that. So we talked about some natural scattering and absorbing. So, like I said, if something's being absorbed, you could just think like a flower's yellow because all the other colors are being absorbed and it's reflecting yellow. That'd be a good example. So, diffraction, we started getting into that kind of stuff. So diffraction is basically like think like the picture of the spoon in water, right? And it kind of looks like it's broken off, and you got, you know, half a spoon, and it seems like it's, but then when you pull it out, it's, you know, a normal spoon. That that has to do with the diffraction. So the variable that we use when we talk about diffraction is n, right? And we were given a bunch of n values for different kind of mediums, right? So she says in a vacuum, n would be 1, but if we were saying like air, you guys probably remember this, it was like 1.0003, and then water was like 1 1/3. I think glass was 1.5. Hold on, I'll find these. 45, she talks about this, and then 45 and 46. So these are index of refraction, right? So index of refraction or diffraction. Hold on, I don't want to be saying stuff wrong here.
On page 46, she has diffraction. Is there a
Mhm.
difference between the two, refraction and diffraction?
That's kind of what I'm trying to see right now. Because I don't want to be saying it wrong. Because I'm talking about refraction, and I looked at diffraction. So, okay. N, let's just be clear, is refraction. So there is a difference for sure. But N, refraction, not diffraction. So yeah, anything that refracts has to do with those things that we were talking about earlier. So like reflecting, scattering, transmitting, right? So the way, let me go back here. The way that we found N is C over V, right? So let's just refraction. C always means the speed of light. And that's always going to be 3.0 times 10 to the 8th meters per second. Right? So then we were able to find those n values, or even velocity if we know the n values, vice versa if we know the velocity. So knowing how to use this equation is going to be important. So let's talk about diffraction then. What's the difference, huh? Does anybody have any ideas about that? Diffraction. It says, with water waves, we know that when they are pushed through an opening, the wave spreads out in a nice wedge pattern. The tinier the opening relative to the wavelengths, the more pronounced the pattern. So diffraction must have to do kind of like we're talking about the slits. You know, we got all these slits. And you have, say it was water, and the wave's just coming straight on. As it hits like one of these holes, it's going to start diffracting and spreading out. Does that make sense then? So refracting, I wish you had like a diagram for it, but I think it's kind of like the opposite. So this is bending around and slowing down, where this is kind of like bending out and becoming more pronounced. Does that kind of make sense? So she asks us, what's the difference between refraction and diffraction? We could say refraction, I guess, is kind of just like a change in direction of the waves when they travel to two different mediums. right? Where diffraction is the bending of waves around stuff, like obstacles or openings, or, it could be anything, right? So does that kind of clear it up? The difference between refraction and diffraction? So refraction is just basically like a change in direction when going from two different mediums, where diffraction is a change in direction from like an object or an obstacle or an opening or something like that. Hopefully that kind of clears that up. So, talked about, so utilize diffraction to measure multiple dimensions of waves. So we can kind of get into this stuff. So one of my favorite pictures that helped me a ton, thanks sweetie, they do, it's kind of like with like two slits, and they have, let's say this is a line, like a dotted line this way, and then, this would be, we'll call this R2, going up to here, R1, right? So you guys know what, this is on page 47 in our notes, and this is a super useful picture because it kind of explains where each variable comes from, right? So actually I want to get rid of this. This would be theta. This distance, so this would be where we'd make, this would be a change in R. Right, you guys know what I'm talking about. So this is a diffraction gradient, right? Because it's bending that light. The light's coming in, here, it gets bent through these little things, and it causes that really complicated picture that they have on the top of 47, where it shows all the, kind of the points of constructive interference and destructive interference, and the the pattern on the screen, right? So that, like she said, these two pictures here are good to kind of break down. So basically what's happening, light's coming from a source, it's going to two different things, right? And then there's kind of holes here at different M values. And as it, closest to the source is going to be the most intense. And it's going to be harder and harder for these, the light to get to these spots as you go out further. So they're going to be less intense further from the central maxima. So you call this central. Right, and it kind of looks like that, this screen, where I knew I drew it somewhere, this thing. Right, where this is 0, 1, 2, and we talked about using this equation to find, the angle. That's diffraction grading. So if they ask you, use the diffraction grading to find M or whatever, or say it's asking, what's the change in R? You'd want to look for 47 and use like one of the equations on the sheet. So the most useful ones to me personally would probably be that sine theta equals the fringe number times the wavelength divided by the distance. That was a really useful one. There was another one where like the y of m. So let me just define this. So if you look on that sheet there, y would be the distance. So y equals, we'll just say the distance from the central maxima to whatever, to your m value, we'll say. So that would be, you know, if in our case, if it was 4, y is the distance from the fourth fringe to the central maxima, or 0, right? So if you're trying to figure out the fringe distance, you know, that's where you'd use y, or the fringe spacing, right? Or change in y is also a similar kind of concept. Equals. I didn't really use this one too much. I preferred. Here, we'll say this other one first. I like this one. Y equals m, or y of m equals m times wavelength times L over d. It's very similar to other ones that we use, and to me that one was easier, right? So then, you know, if you had 4 for your m, you know this would be y for the 4. So the m just means like whatever m value you had, right? And then your R1s and R2s I kind of talked about. So that's just the distance from, like, you know, one slit to the fringe and the other slit to the fringe, right? And so if you want to find that change in R, that was another useful formula. So R2 minus R1 equals m times wavelength, and that also equals d theta m. So this is kind of where this one comes from, just mixing around of equations and stuff. But for sure, this one, like, to me on that sheet, these two are like the most useful. And I'm sure there might be situations where we need to use some of the other ones. Like maybe if we're trying to find the angle from the center maxima, right? That one, I mean, we could use this one, but if you didn't want to mess around with the sine inverses and stuff like that, you could just do theta of m equals m wavelength over d. And if anybody's confused on what theta is, that's just a representation for some angle, right? So I think that kind of covers some things on fringe spacing and utilizing diffraction to measure multiple dimensions of waves. So we usually do that with sound, I mean with light, but it's possible to do with sound, I think. Because we talked about how diffraction kind of works, or not, with sound as well, because they're both waves, right? And then last one for this section, apply the concept of interference and double slit diffraction. So I kind of have talked about that. That has to do with everything on 47. Just remember, if you're gonna do this kind of stuff, like these equations, it's very important to be in radians. Because you could be doing everything right, you have all the right concepts, but you get it wrong because you're in degree mode, right? So that's something we don't want to happen. So make sure if you're going to start messing with any trigonomic functions, like you're going to do sine or tan, or we're starting to work with these fringe spacing and stuff like that, make sure you're in radians, and then, you know, switch back afterwards.
Question.
Yeah.
I thought it was oscillation formulas that we have to be in radians.
Nope.
No?
Nope. That one you'd want to be in degrees, because that's just like your algebra and stuff like that. If you're in like kind of light optics section, or these fringe spacing, or these diffraction gratings, those are all kind of your radian section.
But her notes for oscillation formula says be in radians.
Where does it say that?
For page 35 in our notes.
Oh, really?
Yeah.
Oh, if you're doing those equations, it's not really,
But
is
then
that really necessary? Because you're gonna get the same answer.
I think that you want to be in radians for that because you're not using any degrees for angles in those.
Yeah. But which ones had angles though? That's what I'm wondering. Like we have like 2 pi. Well, I guess that's really only their math, so pretty much are you were saying we'd probably be safe in radians the whole time, do you think?
I think it's only radians and when you're doing oscillations and
It's definitely not.
um
I have, it's definitely
really?
has to be in radians for this part as well. I see what you're saying, and I have it circled and highlighted, so you're definitely right about that. I just personally, when I was doing the homework, didn't
Uh-huh.
ever put my calculator in radians when I was doing this kind of stuff, and it came out okay. So,
Really?
so I'm
Okay.
not 100 on that, but if it says, I mean, yeah, you're right. I see that.
So do you
Yeah.
think we can just leave it in radians like the whole test and we'll be okay?
That's kind of what I was asking, and it seems like to be the case for the most part. Like, is there anything where we need to specifically be in degrees? We're mostly
You
using,
need to be you
yeah.
will need to be in degree for the sine, find the angle. That's the only thing you need to be in degree. So pretty much the rest of the beginning of the test to chapter 4 you can be in degree, and I think chapter 5 when we try and find the angle, that's when you have to be in degree. Or homework 5, sorry.
Yeah, okay, so when we start getting the ray optics and stuff. And does she specifically say to be in degree mode? In any of
She
those?
did, when we were doing the homework, she did come by me and say that you need to be in degrees when you're doing like the
Mm.
homework 5. So
It does, yeah, right here. If you look, Snell's law has to be in degrees mode. So there is going to be some back and forth. So for me on 47, I have in radians in like big letters and circled right by where all those equations would be. And then also on 35, now that Mary says that, I also have radians circled and highlighted. So that's where she really kind of indicates that it's necessary. So make sure, I would say, make sure you're doing radians for those two for sure. But other than that, if you're just doing normal math, like keep it in degrees. Do you think that makes sense?
What pages did you say that was on?
So 47 for the light optics and the diffraction grading, and then 35, it also says, and that has to do with the oscillation equations that Mary was talking about, and those also have to be in radians. So those are the two that I see kind of looking through that specifically say radians. And then on page 61, like Pa was talking about, Snell's law specifically has to be in degree mode. Right, so Snell's law is that the n1 sine theta equals n2 sine theta 2. So like if you have two different mediums with different indexes of refraction, you can figure out the angle at which it's going to come out, right? We kind of did that on our beginning of our last homework assignment.
In week 4, I was doing some of the practice homework and I had my calculator in degrees the whole time and I didn't get a problem wrong. So I'm wondering if that just applies when it's just like 2 pi and stuff in the equation, or how exactly that would work. Because I've been getting them right in degrees with my calculator.
Yeah, and I was kind of, similar with the week 3 stuff. I think it has to do with the trigonomic functions. So if you started trying to do like the sine ones, right? Like sine in radian mode is going to be a little different than sine in degree mode, right? Because it's like the difference is basically in radian mode, the circumference of a circle is 2 pi, where in degree it's 360. And so the sine ends up being in radian mode. So your numbers are way different, if that makes sense. I don't know. If anybody did trig, they probably know what I'm talking about. But I'd say just go with what her notes say, right? Just rather be safe than sorry, right? Like I'd rather say do radians because that's what she said to do rather than, oh yeah, I didn't do radians, it was fine, so you're gonna be fine. Like I can't guarantee that. And she specifically, indicated to use radians, so I think it would be a good idea to make sure that you switch it during those problems.
I think you're right. And then when it says to switch to radians, we definitely have to do it because like for example, if you put sine 45 in for degrees and then sine 45 in radians, they're different.
Yeah, like sine 45 is like pi over 4 in radians, where in degrees it's like something totally different, right? It's probably undefined because you can't do sine of 1.
Yeah,
What?
so I
Yeah.
think for the start of the test, just leave it in degrees, and then when we get to those problems, like on the cheat sheet under diffraction and stuff, turn it to radians.
Yes.
Yeah.
And same with those other ones that Mary was talking about, so the oscillation equations. But like I said, that was mostly algebra, so I was confused. Maybe it has to do with the square root, like in the speed equation. I'm not 100% on that. But anyway, like I said, if it says radians, I would, lean on the side of using radians rather than, thinking, hey, I was fine last time, right? So I should be okay. We'd hate to have it actually matter on the test and then you get a problem wrong because you simply, didn't switch your calculator over. That would suck, right? So just be really careful with those. We talked about reflection and refraction, right? So reflection was bouncing off something,
Wait,
refraction is
so
kind of going around. What?
for the oscillation questions on
Mhm.
the cheat sheet, is that the ones all under linear SMH on the front side?
Linear SMH. Hold on.
Or SHM, sorry.
Yes.
Okay, thanks.
Yeah, because that stands for simple harmonic motion. I'm pretty sure. So yeah, that's the area, and that's all those are in that like red box on 35. But yeah, good shout because knowing where those are and where everything is in this that cheat sheet is really useful, for sure. Yeah, she's got everything on here. I wanted to talk about open, closed, open, open. I think I missed that. Because that's like seemed like kind of a tricky thing, right? So we only have a few more here on 5, maybe then we can go back to that and then we can just kind of go over most of the short answer questions that I didn't necessarily go over already. So differentiate between reflection and refraction. We said reflection was when it bounces off, right? And refraction is when it like goes around or is like moved by an object or kind of gets pushed through a hole, right? It's refracting. It's moving out of it's acted upon by an outside force, kind of. Think about it that way. We can relate reflections to mirrors and refraction to lenses. So lenses reflect light, like I said, because they move it. So if it goes through a lens, okay. I'm going to say a trick that I've been telling other people. I don't know if it makes sense to them, but it makes sense to me. If you have, so converging and diverging are forms of refraction, right? So converging means if you think converge, you think like come together, right? So if light's converging, it's kind of condensing. Where if it's diverging, you think the word diverge means like spread apart, right? So the way I remember, okay, let me back up a sec. Concave, concave, I think of cave towards, right? Cave towards me, like it's caving in. And then convex is like just the opposite. So if you think cave and kind of curve in. That's how I remember those two. And then if you're trying to think which one is the converging, which one's diverging, convex starts with CONV, like conv. So that goes with converging, CONV. So the two, they are very similar. They go together, right? So convex, converge. Am I saying that right? Convex, converge, concave, diverge, right? Convex will make a virtual image. Concave will make a real image in a mirror. Where in a lens, it'll just go through. And in converging lenses, so that would be convex, converge, concave, diverge. So CONV, CONV. That does work. So if you kind of think about it, those are like the bowed out ones, right? They're not caving in. They're like pumped up. Those ones are going to make a clearer image, right? Converge. Like if you think about the laser that we just did, if your laser started getting too like spread out, too big, you had to use one of those lenses. You in fact had to use a convex lens to try to get that light to fit in the penny, right? Where if you wanted it bigger, you would use a concave lens. I think that goes over most of that. There were some confusing things when it came to like 16, problem 16 on the most recent homework. And Shannon did email everybody about some like updated answers and stuff. So I kind of just wanted to show some things. So if we had like one of those ray diagrams, right? This is your, oops, I keep doing that. This is your object, right? This is the height of the object. I like to think about this as like a graph, right? So this is the x-axis, this is the y-axis. If your image is somewhere, you know, down here, right? But it's a converging lens or whatever, where they're all kind of hitting to this point, right? It's not dotted lines, it's solid lines. This is going to be a real image that's inverted. So the way I think about this, if you have dashed or dotted lines that converge to make an image, it's virtual. Because the actual rays of light from the source are not what's creating the image. You have to like kind of go back and backtrack or use a reflection or you know what I'm saying, right? If you see dotted or dashed, that's going to be virtual. Another way you can think about that, if the object or the image, see in this case the image was over here, that would mean it would have to be a virtual image, right? It would have to, if it's on the same side as the object and it's going through a lens, it's going to have to be virtual, like some kind of reflection, right? But if it's on the opposite side and you can see it's all dashed lines going to it, it's going to be a real image, right? And there's on page, because I'm going to get into this part next, on page 65 they talk about sign conventions when using the thin lens equation. So it's really important to keep your positives and negatives straight when you're doing, how do I explain, when you're doing the thin lens equation because it matters what if m's negative or f is positive or if d is negative, right? And all that stuff matters because that tells you about the image, right? So another thing, if say here we'll get rid of all this stuff because it's getting confusing. If the image was up here, right, but it's dashed lines going to it, just to kind of reinforce that. This one would be virtual and it would be upright. So the way you tell between inverted and upright, so upright, if we call this the x-axis, above the x-axis is going to be upright or a positive image height. Where if it's negative or it's below here, negative image height, it's going to be inverted. So inverted, negative image height. And then if you're is it possible to be virtual on the opposite side? Or can I just, you guys think it, let me look. Because that'd be easier just to say, if you have an object and the image is on the same side, it's probably virtual. And if it's on the opposite side of the lens, it's probably real. Does that kind of make sense? Because if it's on the same side, it would have to be a reflection of some kind. And then I also want to talk about D values. So if D is negative, it's virtual. Where if D is positive, it's real. So that, yeah, so I'm right. So if you're going this way, right, you're negative. Like if these are all x values, this would be 1, 2, 3. This would be -1, -2, -3. Right, so if your image was somewhere over here, you'd have a negative D value. Where if it was somewhere over here, you'd have a positive. Right, so negative DI, or distance of the image, is virtual, and positive is real. So that's important stuff to know, or pay attention to. And I talked about this with some other people and stuff too, but you don't have to worry about it too much. Like as long as you are following your numbers and signs and the equation to a T, you should be okay. So if you have, this is the one we're talking about here. So height of the image over height of the object equals a negative distance of the image over distance of the object. So this negative is important, and knowing and keeping track of them all so that your final answer comes out, you know, negative or positive, is important to keep track of. I wanted to clear up some things when it comes to drawing the rays. I know, you know, it's probably not going to be one of the most popular of the short answer questions that people are picking, but I just wanted to talk about. There's two, so like I said, diverging is concave, right? And converging is convex. And we have two sets of rules for the lenses. I just wanted to say you cannot use those rules for mirrors. There's a separate set of rules for mirrors, and those are on page 59. And they talk about concave. She gives 3 kind of rules, or what to do with each angle, or ray. And then does the same thing for convex mirrors. So this is something I wanted to clear up, because I know there's been conflicting explanations about this, and this is what makes most sense to me. If you have a concave mirror, talking about mirrors here. If you have a concave mirror, I mean, it still technically has 2 focal points, but we're not going to use this far focal point. It's only going to be this near one, right? Where the opposite is true if you have a convex mirror. In this case, the focal point that we're going to be focused on is the far one. So light's coming in this direction on both of them. So when we're drawing our waves, like it says parallel through the focal point, and for concave, you're going to go parallel back through this. So you're going to go parallel in, you're going to go toward this, right? And this is through focal point out parallel. You're going to go like this, right? And then through axis with equal and opposite reflection. If you guys struggle with this one, what I would like to do is measure like you know the height of the object. You know that if you do the exact opposite of that, so here, let me get rid of some of this other stuff. If you know the exact height of the object, right, and you have the ray that's going to hit the lens or whatever, and it's going to come out equal and opposite, it's going to have to hit exactly the same distance away on the bottom. So then that way you don't have to break out a protractor to try and find these angles here. Hopefully that kind of helps, because I know it's kind of tough to draw. And if you were choosing to do that short answer on the test, I guess those are just some tips. So okay, does that pretty much kind of cover everything? Does anybody have any questions about anything before we go into the short answer problems? No? See, why is it doing this to me? I'm clicking on it. Well, oh, I see. I scrolled down. I'm down. So, we pretty much talked about all this stuff, excuse me. We talked about wave types and terms, speed and equations, talked about sound and hearing, talked about intensity, pinch, timbre. Did we talk about timbre? I don't think we did. Can anybody tell me what timbre is?
That's connected to amplitude.
Is it?
I mean, I asked Shannon today, and she
Mhm.
explained it to me based on example of ukulele and guitar. And
Okay.
she was saying that, for example, like because of the length of the string on guitar is longer,
Yep.
the timbre would be bigger because amplitude would be bigger, the sound would be deeper.
Okay.
So she explained it like that, but I don't know if
So is timbre kind
you.
of like pitch then? Because it would be, yes?
I mean,
Oh, sorry.
I'm
No,
sorry.
go ahead.
I saw timbre as tone, or
Oh.
like that's how I perceived it.
Oh yeah, that's tone. I'm sorry.
What's the difference between tone and pitch? Right? And don't they sound like the same thing? Like if it has a low tone, it's like ooh, but if it has a high tone, it's like ah, right? And the same thing with pitch. Am I right or no? Like I'm confused. Let's see.
They
Yeah.
might be different in frequencies because is it their it's their page 41.
Mm-hmm.
So we have there in connection that high frequency has a high pitch, but timbre it's a tone and it's connected to amplitude, not to frequency.
Okay. The tone quality. Timbre distinguishes different types of sound production. Okay. So that kind of makes sense. So if you think pitch, think frequency, think shorter wavelength. If you think timbre, think amplitude. It's kind of what you're saying?
Yeah, yeah, I meant that, for example, like on guitar, you would have a bigger amplitude
Yeah.
than ukulele, and timbre, like tone, would be deeper
Yeah.
because tone and timbre is basically the same. They connected
Mhm.
to amplitude, but pitch connected to frequency. So higher frequency will give us a higher pitch,
Mhm.
while the lower frequency will give a lower pitch.
Okay.
And we have their like diagram on their page 41 for different musical instruments,
Yep.
and like they kind of like show this.
Yeah. They talk about it on 41. So timbre, think I understand what you're saying now, I think. So it's like a guitar is like a lot more rich of a tone and it has a lot more things going on rather than kind of like a plunky, little bit more like, you know, twiggy sound of a ukulele, right? Like a ukulele is going to be have a smaller amplitude because it's a shorter length of the string, is what you're saying. Where a guitar is longer and that, you know, chord is going to be able to have a larger amplitude where it'll have kind of more timbre. So it'll sound a little bit more full, a little bit more rich, a little bit more. I think I understand what you're saying. And that makes sense too. So if you had like a choir full of a bunch of voices, that's when it sounds really full, really, and it has a lot of timbre. Would that make sense?
Yeah.
Okay. Cool, that helped me there actually.
Did we have a chance to talk about intensity? I don't remember, but did we?
I don't know if, yeah, we can go back. I think intensity is very similar to loudness, but like volume is like subjective, and intensity is not. So intensity is just like how intense the sound wave is, like measurably. Like so the what we use to measure intensity is decibels. So intensity it says is power over the surface area. So how much power, or remember we said power was like watts, right? Like joules per second. How much power over how much surface area? And it means like how intense. So like a bomb has a ton of power and all its surface area, right? So it's going to be pretty intense. Where something like a mouse, you know, isn't really going to make a ton of power or even that big of a surface area, right? So it's not going to be very intense. But relative to the mouse, it might be. You know what I'm saying? So that's where, like, volume or loudness could be subjective, but the actual intensity is not. Does that make sense? Because, like, to a mouse, something with low intensity might be really loud, right? But to us, we could barely hear it. So
Yeah.
you can't be like, oh yeah, you can't use loudness as like a measuring or even comparison because everybody's just so different.
Yeah, and also she said, I mean, could you like give more explanation to the why intensity is not the same as intensity level? Because she said it's just compression to like threshold of human hearing, but I mean, yeah, it's still like not clear.
Mhm. So, I guess I'm kind of confused. Um, like
That's
you,
a page 24,
yeah,
and there we have like just the
loudness and
mm-hmm.
intensity. hmm So, loudness, like I was kind of saying, is subjective, which means like it's like your opinion, right? Like to me, I could say, man, that was a really loud noise, but to you, you're like, hey, that wasn't loud at all. I'm used to way louder noises. We can't we can't use that as like a unit of measurement because like I said, it's an opinion. So what we use to measure the air quotes loudness is intensity, right? So intensity is power divided by surface area. So sound waves, like I said, travel in spheres, right? So the area of a sphere is 4 pi r squared. So that's where the equation power over 4 pi r squared for intensity comes from. So it's just literally how much power a sound wave is traveling with. Where loudness is just how each individual or each organism perceives that intensity, right? Like in my eardrums, like I'm personally, when we did that sound test, my age of hearing was like 40 years old. Like I had terrible hearing. So to me, stuff isn't going to be as loud as it is to somebody else. Does that make sense?
Yeah, thank you.
Mm-hmm. So, okay, you guys want to get into the couple of questions? So let me look. I wrote them down. We kind of talked about the spider one, right? So I could just kind of walk through how we solved that if somebody missed it. So let's see, that was at the end of the first section, right? Guys, help me out. What page? Okay, never mind. So page 27 has the questions with the spider. It's the first question. So it basically asks, all spiders are very sensitive to vibrations. An orb spider sits at its center of a large circular web and monitors the radial threads for vibrations. If an insect gets snagged by the staking lines, it'll feel them. Assume these threads are made from silk with linear density. So what do we know about linear density, right? That's mu. We have a couple of equations with mu kind of earlier back in this part of the beginning, right? There was that main one that we talked about that was velocity equals the force over mu. Oops. Right? So I would assume the spider problem is going to be similar to this one. So we're going to need this equation. We're going to be given a linear density. In this first problem, it was like 1.0 times 10 to the minus fifth. Linear density is always in kilograms per meter. And I also wanted to mention too, don't forget to convert. Like if something's in centimeters, convert it to meters. Like always go to meters, always go to kilograms, always go to seconds. Things like that. And we were given a force as well. So force is always going to be in newtons, right? So to find and then it also said that the insect landed distance was 30 centimeters from the spider. So what we did to find, because we're trying to figure out how fast is the spider going to know that it landed, right? So we need to know the velocity or the meters per second that the wave is going to travel across the silk to hit the spider, right? And then we know the distance in between that area. So once we know the speed, we can figure out how long it would take, right? So that's kind of the process. So you end up going 0.4 newtons over, what was it, 1 times 10 to the minus fifth kilograms meter. You get a velocity of 200 meters per second. So that means, right, in 1 second, the vibrations are going to travel 200 meters. So that's really quick, especially if we only have 30 centimeters to travel, because you could say that's equal to, you just move the decimal over twice, so 0.3 meters, right? So if it can travel 200 meters in 1 second, it should be able to travel 0.3 meters pretty darn quick. So the way I figured that out is another thing called dimensional analysis. So that was in chapter 1 and stuff. If I'm in meters, and I know this is meters per second, you want the same unit on the bottom of the next one, right? So they cancel out. So in this case, you would say 1 second over 200 meters, right? The m's cancel out. We're left in a time, which is what we wanted, and we end up, when you multiply these and divide it by 200, I got 0.0015, 15 seconds. So in problem 1, that'd be the speed of one of the spiders probably, and then we'd have to figure out the speed of the other one and determine which one would feel that vibration first. Right? Does that make sense to everybody? So this would be for 1. For 2, we kind of talked about already, and we were I was wrong about one thing, so I'm just going to restate the right answer. When it asks to graph position versus time, I don't know how it's going to be. We might have to make a table of values for x and y. Know that this is always the x, this is always the y. And we're going to have time on the x-axis and position on the y for problem number 2. So it's probably going to be, something like, maybe like one of these things, if I had to guess. Because as time went on, it would go up to the higher position, down the lower, because we're doing oscillations. So it'll probably look something like a transverse wave. If I had to guess. I could be totally wrong. I don't really know the context. All it says is graph time versus position versus time. Number 3, solve for amplitude, period, spring constant, maximum speed, and total energy. So did anybody have like one of these problems that they would like kind of want me to go through that had to do with solving for like period, amplitude, or spring constant? 'Cause I could try doing that.
I mean, because we can just redo like our homework.
Yeah, I would recommend that too.
Yeah.
Just if you were kind of, there are any specific ones though that you were maybe struggling with that you just wanted to see somebody go through it again.
For week 3, problem number 4.
Mm-hmm.
Yeah.
Okay. Week 3, problem 4. Which one? Just all of them? Should we just run through it?
Yeah, we can just go through it if you don't mind.
Yeah, sure. Cos 10t. Okay, so the way I'm thinking about this is I recognize this, right? This is that position equation, right, where it asks a cos, what is it, like 2 pi, yeah, 2 pi ft, right? It's in the same format, right? But instead of a, we got a value for a, and instead of 10t, we have all this stuff for 10, and we still have the t. So that's the way I thought about it. So let's do A. It asks for the amplitude. Well, that one I think is pretty easy because this A means amplitude, and in this problem it's filled in already. So I think the amplitude must be 2 centimeters. Right, so that one's a gimme. Let's see, B, the period. So there's kind of two of these, right? But I don't think we necessarily need that second one, because we could just do this, no, I think we do need that one. I just want to double check how I went through it. 4B, yeah, okay. So what do we know? What was something I said before earlier? 1 over T equals frequency, and vice versa. 1 over frequency equals T, or period. So if we're trying to solve for period, and we don't have any way of getting to period, well then you ask yourself, do I have any way of getting to frequency? Because if I know frequency, I know period. So in this case, there is a way to find the frequency. So we know that 2 pi times the frequency is equal to 10. So 10, right? So that means if I divide both sides by 2 pi, you should get the frequency, right? So it'd be, what is that on the calculator? Well, I could look at my work. I get frequency equals 1.59, right? So if we have that, we can figure out T. So 1 over 1.59 is going to equal T, which equals 0.63 seconds. Period is always seconds. Frequency is always hertz. So those are two to kind of remember. So that's the answer for B. So we got A, B. Let me circle these. What's C? C's asking for the spring constant. Well, how am I going to figure that out, huh? I know I have the amplitude. I now have the frequency, right? So maybe I could use one of these other equations in the red thing, in the red box, right? So spring constant. It looks like was I given a mass? No. Well, then I can't use that one. So that's kind of the process, right? You kind of write down what you have, what you need to find, and then you go look for the algorithm. And if, you know, you're missing stuff, maybe you're gonna have to try and like look for a different one, right?
Gave us a mass.
It did give us the mass.
Yeah, in the problem
Oh,
it's 50
okay, cool.
grams.
My
Yeah.
bad. 50 grams. Thank you. I was thinking, like, how am I gonna solve this if they didn't give me math? Okay. 0 point, so the equation that I'm gonna use is T is the spring, what do they call it? The spring equation is what I think about it as. It's T equals 2 pi times the square root of M over K, where K is the
I'm
spring
sorry to
constant.
interrupt you, but I have a question.
Yeah.
So, like, how do you know if you should use the F or the T? For
What do
like
you
the
mean
spring?
for C?
Yeah, because like there's like an F and a C. They're both for spring, right? So, like, how do you determine which equation to use?
If you have all the pieces for either one, I think it's kind of up to you. But I'm
Oh,
kind
so
of,
it doesn't matter?
which one's with the F? Oh, I see it to the left here.
Yeah,
Yeah,
so
so
like,
the only difference really, right? So if I have this equation, this is for T. Well, we know that frequency is inversed, right? So if I wanted frequency, I could just inverse everything. So I could say 1 over 2 pi times the square root of K over M. Do you see what I'm saying?
pretty much, yeah, so it doesn't really matter which one you use.
Yeah, they're
That's
kind
my
of the same thing, but just flipped. Does that make sense?
thank you.
Mm-hmm. So I don't know. I always just use this one because it was in the red box. and I decided to use this one because we had a value for t. But I suppose we did find f2, so we could have. You're right. Like we could have used that one as well. I'll just kind of keep going what I was doing. Remember, always convert. So you want kilograms, meters, seconds. You don't want grams or millimeters. So always remember to convert. So in this case, we need to get to kilograms, so it's got to go over 3. So we end up with 0.05 kilograms. Right? So now let's plug all the numbers in. Or, actually, if we kind of go back, another thing that I like to do before I plug in all the numbers is I like to rearrange the equation. So I kind of remember from earlier that K is equal to M divided by T over 2 pi squared. Right? So let's plug in what we know. So K is going to equal that 0.05 grams divided by our T, which was 0.63, divided by 2 pi squared. So if you plug that all in, you should get, I don't have my calculator right now, so I'm just going off what I did. I end up with K equals 5. Oops. Let me grab my calculator just to make sure that I did that equation right. So we'll do. Does anybody know, do I have to be in radians for this stuff or not?
Believe
Yep.
you do.
Mm-hmm. Definitely do. So 0.63 divided by 2 pi. This is how I type it in. I did 0.63. So I kind of do this 0.63 divided by the 2 pi, right? And then I square that number. So square it. And then you can do the 0.05 divided by that number, right? And for me, to be honest, if I'm in radian modes, I'm not getting the right answer. Oh, that's the other thing. I've noticed this problem a lot as well, so be very careful with this. If you divide as 2 pi altogether, like you just type in 2 pi and no parentheses, it's not going to give you the right answer. So you either have to do parentheses around the 2 pi or split them up. So I would do 0.63 divided by 2 divided by pi, and then you square that, and then you do your 0.05 divided by that. And then you end up with 4.97, which rounds up to 5. K is always newtons per meter, so it'd be N over little m. I'm pretty sure I'm right on all that stuff. Yeah. So okay, let's do the next one. That's C. Let's do D. D's looking for the maximum speed, so I know I have like frequency. Now I have a spring constant. I have a period. So what equation can I use to find the total energy that would also help me, or that I can also use pieces that I already have, right? So if you look back, I think, what one did we use? I think we used the kinetic energy one, if I'm not mistaken. So we know kinetic energy. So the amount of kinetic energy equals the amount of potential energy, like when they're both at 100%. Like, so you have like a set amount of energy and it switches back and forth between kinetic and potential, right? So the equation I used Ke equals 1/2 times m times v squared, right? And we, I don't think are given a velocity, are we? Is this the one I used? No,
So
that's for
this was
E.
by far the most challenging one for me. We used the equation, but it was 1/2 times K times A. And then we ended up in joules.
1/2 times K times A. I think I'm looking at E. We're solving, what are we solving? Not,
Yeah,
oh, Maximus,
for K,
what? For
for
E?
K. Yeah.
Yeah, so I think we'll, hold on, we'll hold off on that, and we'll do the speed first. The maximum speed. So, that's why I used that one, I think, because I just solved for velocity like the previous problem. And so I'm like, well, then I'll just use this equation. But so, backing up, let's find the velocity max. And I think there was an equation for that one in our red box. So minimum speed was 2 pi, so V max 2 pi times frequency times amplitude, right? And in this problem, we know the amplitude and we know the frequency, so we should be able to solve for V max. So V max, because remember, like I said, velocity is kind of like speed for us. I mean, if you go further in physics, there will be a point where, you know, they're different things, and they are different things. But for now, like this test, if you see speed, think velocity, right? 1.59 was their frequency, right? And their amplitude was 2. Oops. What did I do wrong, right? This is in
Yeah.
centimeters.
Convert.
Yep. So I'd have to convert this to, it would go to 0. Just, hold on, let me back up. No, yeah, 0.2. So then if you multiply those all out, I ended up with a velocity max of 0.2 meters per second. Is that right? I think so.
Yeah.
Yep. Okay, so now let's go back to E. So I use the kinetic energy one, and I think, you know, Jeremiah, you wouldn't be wrong using the other one. Like I said, it's kind of subjective which equations you use sometimes, because they all have similar variables, and if you have the values, you know, you can kind of pick and choose which one you feel more comfortable with in some cases. So in this one, you know, we could find the potential, you could use the potential energy one, which would be the mass times the gravity times the amplitude. You could do that. For me, we just found the velocity at the minimum, or at the max, right? And at what point in an oscillation is the velocity going to be at its max, right? Because we kind of talked about this earlier, where when it's at 100% kinetic energy, it has its maximum velocity because it's, you know, moving at its highest speed, and then it starts to slow down, like we were talking about the pea in the bowl, right? As it comes down the bowl, it gets faster, 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 and then when it crosses that rest point, rest position, it starts to slow down again, right? Until it gets to the top, stops, 100% potential energy, and then it goes back down. So the point where kinetic energy is the highest would also be the point of the maximum velocity. So that's why I thought, okay, well, I'm going to use this equation. The KE equals 1/2 times mass times velocity squared. We know, like I said, just to reiterate, kinetic energy goes with maximum velocity. And minimum velocity or no velocity would go with potential energy. Right? That would have to do more with gravity. That's why gravity's in that equation if you have potential energy. Because you have no velocity and you're relying on gravity to start pulling you back down again. Right? So this one, let's find the total energy. Because right now, if we're at maximum velocity, we're at 100% KE. So that's equal to our total energy. So KE equals, I like to write it this way just because it's easier for me, 0.05 times 0.2 squared over 2. You see how I did that? I just kind of took the 2 and put it over. Because timesing by 1/2 is the same thing as dividing it all by 2. So if you calculate that, you should get, look, should get
Can I ask a question?
0.01.
I'm
Yeah.
not sure that I understood. So when we have our maximum velocity, we can use it only in maximum kinetic energy, yeah?
Yes.
Okay, thank you.
And that's because the point where there's 100% kinetic energy is the point where there's also a maximum velocity. Like, it kind of goes back up to talking about, where was it? Like the P bowl. I think I talked about it real early on. Yeah, like this stuff. So here, we're at 100% potential energy. Here we're at 100% kinetic. Back up at the top, this side is 100 potential again. So that ratio between the two, starts to lean, more towards kinetic as you get down to here. And then as we start going back up, it starts going back to potential. And then this point, if you think about it, the P, where is it going to be moving the fastest? It's probably once it gets to the bottom of this hill. Like if you're on your bike and you go down a big hill, you start gaining speed as you come down, and then and say there's another hill in front of you, you're gonna have a bunch of speed here. Right? Oops, I'm just deleting stuff. You're gonna have a bunch of speed here, but you're gonna start slowing down as you get to the top of that hill. And eventually, if the hill is high and steep enough, you'd probably run the risk of start running back down again, right? So that's your potential energy. Your kinetic energy going up the hill is turning into potential. And then once it stops, it starts getting back into kinetic the other way. I hope that explains it. I gotta go way back down. We made a bunch of notes. How can you sit and listen to one guy talk for so long? Yeah. Was that all of them? We got one more. So now we can just use that original equation. So it says the velocity at t equals 0.40 seconds. So that just comes back to that equation that we're given. I'm sorry. I'm lying. It's a different equation, right? Because that has nothing to do with velocity. So sometimes you gotta look and be like, okay, wait. I think it's this, but let's double check myself, right? So it doesn't have anything to do with velocity. Let's look for another one. Well, it looks like this speed one here. So this v equals 2 pi f times the square root of a squared minus x squared, right? So I know velocity, we know the frequency, I know the amplitude, but I don't think I know the x value yet. So maybe that's where that initial equation comes in. Like, oh yeah, it is. Okay. X equals 2.0 centimeters. So let's convert that. Right, so we're at 0.02 meters times the cosine of 10, and we're given t now of 0.40. So we're going to have to do that 10 times 0.4, right? So then if you plug that into your calculator, you should get a value for x, and then we'll be able to figure out the speed at a certain time. Right, so this x right now just means, like, if we're talking about this ball, you know, at 0.4 seconds, when we find x, we're finding where along this bowl is the ball going to be. So we're saying right now at 0.4 seconds, you know, this is where the ball is. So we figured out the position of the ball. Right now we have to figure out the speed that it's traveling at when it's at that point, right? So this should be 0.2 times the cosine of 4, which would be, what cosine of 4 is? Let me just look. X equals negative 0.013, right? So now I can plug that in to this to find my speed. So we got velocity equals 2 pi times, our frequency was 1.59, our amplitude was 0.02, right, because it was 2 centimeters, yeah, 0.02 squared minus a negative 0.013. Right, so a negative minus, this ends up being a positive. Okay, and then you can plug that all into your calculator, and you should get a velocity of 0.15 meters per second. Right? So that should have been all of them. That kind of help explain some stuff, Mary, or do you want me to go through more?
No,
No?
this helped.
That
Thank you.
helped? Okay.
Yeah.
Yeah, so just kind of having a process, right? Like, it doesn't have to be the same as mine, like whatever works for you, but having that a process down, like how am I going to go about solving problems like these, right? If you kind of just look at a problem, it's can be really, it's a lot, right? Like if you don't break it down step by step, right?
Yeah.
It can make
Thank
it
you.
easier, step at a time. Yeah. Okay, so that was 3. We talked about that, like going through air, like if this was, you know, air, and then glass, and then water. Did we kind of talk about this one? I don't think we did. It just has to do with that n value, like the index of refraction. You kind of figure out, you know, what's its velocity going to be. It's using that n equals c over v. And you use that, you figure out what velocity is going to travel through, and then you probably have like a distance. So you figure out how long it's going to take to go through this one, how long it's going to take to go to that one, and then you add them all together. Should we go over that one, or do you guys kind of get that one? Everybody feels pretty good about that?
Yeah.
Yeah.
Yeah, I'm good on that one too.
Okay. Then, so that was 4, so that shouldn't be too bad. 5, I think we kind of talked about already when it comes to finding m. They're the angles for m. So that would be probably using that sine of theta equals m wavelength over d. This equation. It's a useful one. I'm starting to memorize all these, saying them so many times. Not just like in this meeting, but like over the past week or two. Kind of nice. I just memorized a unit circle too. I've been pretty proud of that over the past week. So then we need to talk about, for 6 was a converging lens. So converging means convex, right? And it's a lens, so light's gonna be able to pass through. Draw a ray diagram, say if it's real or virtual, inverted right side up, and what is the magnification? So that's your M value. And that's gonna be equal to the height of the image divided by the height of the object, or the negative distance of the image over the distance of the object. Right, so like that, those ratios. And that's kind of where like the height of the object doesn't necessarily matter. Like if they're not given, you kind of just have to pick it in your ray diagram, because then the height of the image is going to be a certain ratio away, and these will be the same ratio, and ultimately it should end up with the same n value no matter what height of the object you used. Right? I'm personally probably not going to pick 6. So, I mean, if you guys want to do that and you feel better about drawing, by all means. And if you have any questions, definitely let me know.
I personally have like a hard time like with the height, like figuring out the height of the virtual or the image, like when it's not given. So like number 12 on week 5, like it's not given a
Yeah.
height.
And that's kind of what I was saying. So you kind of just have to, it's like up to you. Like you could pick 6, you could pick 5. I know like you tell people that and it's usually they're like, well, what the heck? And that has to do with what I was saying. So if you pick, 6, and the ratio is supposed to be 1/2, this is going to be 3, right? By after you do all the ray diagrams and everything. But where, say this was like 7, this is going to be 3.5 then. It's all about that ratio in between and not necessarily the actual, height of the object, height of the image. Does that kind of answer your question a little bit? So for 12, let me look. So this was this last week that we were working on?
Yeah.
Yeah. So 12 was just drawing that ray diagram, right? And it was that, it was a, yeah, convex, converging, convex lens, right? And we weren't given a height, right? But for me, I drew mine on graph paper. I just picked a height of 1, 2, 3, 4, 5, right? I just picked 5 squares. So then I ended up with, after I did everything, my height of my image ended up being like pretty much exactly 2.5 squares, right? So then if you do 2.5 over 5, you end up with like the 0.5 that, it was supposed to be, right? And if you followed your scale really good and you did everything else right, then you can figure out the other stuff, Do you kind of see what I'm saying? It doesn't really matter what it is, like what you pick. It's just about doing the rays right, making sure you're really precise, because then you'll get a ratio between the height of the image and the height of the object. Does that kind of
Yeah.
help?
Yeah, that helps. Thank you.
Mm-hmm. So, and then 7 is a diverging lens. So we talked about, I like the conv. So converging is convex. Like that's how I remember. And then you just know the other two or have to go together because there's only, 2 other options. So you have diverging is concave. And this is only for lenses. For mirrors, if you try doing this with mirrors, it's not, you're going to confuse yourself. And for mirrors, I would just remember, concave and convex. And even, I would even suggest, where she kind of does the instructions of how to do the ray diagram when it comes to mirrors, writing like This one's convex, concave. I mean, you can see it, but just having it down so that you know. And then knowing that this would be a converging mirror. You know, convex mirror, like bending away from you, would be a converging, right? Where, wait, are mirrors backwards? Like, hold on. This is what I'm saying with the converging and the diverging with mirrors. Yeah, so it's the opposite with mirrors, which makes sense because the light isn't going through; it's coming back, right? So if they say, let's just think it's the opposite with mirrors. With mirrors, I just wrote it above those pictures, like which each one was, like convex or converging, you know, just so that way when it came up, like I had directions there, and then I could look at the problem and be like, oh, it's a converging mirror, so it has to be this one, right? So I think mirrors are a little bit different. It even says it right above here. So it says the incident rays diverge from a convex mirror, but they trace back to a focal point. So it's the opposite. But I think we're mostly going to be tested on lenses just because mirrors are complicated and kind of confusing. I mean, I wouldn't put it, you know, be prepared as best as you can for mirrors and lenses, but I would say put more of an emphasis on knowing, you know, lenses and the converging or diverging, convex, concave. So this is, let me just reiterate that this is just for lenses. Would be apostrophe? Yeah. So then there was one last one, and that was just on the question 16 in the homework. So it had to do with this guy, the 1 over distance of the object plus 1 over distance of the image equals 1 over frequency. And that also, so you need this one to find, sometimes you need the distance of the image probably, right? Like you're given the object and you're given the focal length, but you need to find the distance of the image. That's usually the case. And then you have to go use the second equation, which is m equals hi over ho equals negative di over do. And this negative is important. So if I could just go through like a really quick example, maybe we'll do 16a, because that one was kind of confusing for some people. And I know she changed the answer on there. So let's just go through the process, right? What do we know? Object is 2 centimeters tall, so height of the object equals 0.02 meters. It is 40 centimeters in front of a converging lens. So okay, it's a converging lens. So distance of the object, we'll say 0.4 meters. We know that it's a converging lens, which means it's a convex, right? Convex lens. So what does that mean? We know converging means real. It's going to probably make a real image in a lens, where diverging is going to make a virtual, right? So if we look at our sign conventions, we can already probably tell that it's going to be a virtual image, so DO is probably going to be negative, right? I mean, sorry, real. DO is positive, and that's what we're given. So we know that it's going to be a real image, so we can already write that down, right? Next, what else do we know about 16a? We know the focal length. Focal length equals 20 centimeters, so 0.2 meters. I suppose you could have left this in centimeters. It was just a habit for me to switch it to meters. But okay, let's do that first one to find the distance of the image. And then we'll use the second one to find the height of the image. So the first one is 1 over 0.4 plus 1 over di equals 1 over 0.2. Right, and I kind of do this trick sometimes. So, well, first we'll minus this one. So 1 over di equals 1 over 0.2 minus 1 over 0.4. And so for di, there's an inverse button that can kind of be useful. So you can just type in 0.2 and then hit the inverse button. I don't want to confuse people, so just leave that alone for now. And then we'll minus 1 over 0.4. Right? And then we get, if we inverse that, we should get for hi. Hold on, I just want to double check my work. 16a, you get 0.2. Right? No, sorry. 0.02. Yes. No, I'm looking at something else. I'm sorry. Be 0.4. Because this ends up being 2 over 0.4 minus 1 over 0.4. You just get 1 over 0.4 and you inverse that. Yeah. So I got 0.4 for di. And if you have trouble putting that in a calculator, you know, I could show you too. There's an inverse button. Otherwise, there's like a fraction button too. Depends on what calculator you have, obviously. Just knowing how to, but I would hope you guys understand how to use your calculators, but they can be tricky. So I would say the main thing I was getting caught up was in this whole dividing by 2 pi. So if you're going to be really careful about anything when it comes to calculator stuff, I would suggest just splitting up that. If you're dividing by 2 pi, split it up. So divide by 2 first, and then divide by pi. If that makes sense. So okay, now we have di, and we can use that to find hi. So we have hi over, what was it? We said ho was 0.02 equals negative 0.4 over, oops. No, yeah, 0.4 over 0.4. So yeah, this one ends up being kind of cool because, you know, this ends up being negative 1 over 1 and it's easy. But we'll just do, I'm going to show you the cross multiplying, right? So I like to keep this negative with the top one in, with fractions to keep myself straight. So you cross multiply. If you ever have 2 fractions and an equal sign in between, you can cross multiply. So you can say negative 0.4 times 0.02 should give you a negative 0.008. You have 0.4 hi. So if you divide that by 0.4, you should get an hi value of negative 0.02 meters or negative 2 centimeters. Right? So that's kind of an example of 16 and using the thin lens equation. So I think that's all those short answer problems. I think we covered pretty much everything on the study guide. Does anybody have any questions or anything that they want me to maybe try to go over? Like I said, I'm no expert, but I'm, you know, doing my best here, I guess. Does everybody feel pretty good?
Yeah, I think we're gonna do good on this test.
Me too. It seems
Yeah.
like most people kind of got stuff. You know, I can't see her making it too hard. Like she said, the homework problems are going to be a lot harder than the test itself. You know, we get all our notes, so if you know, and we're
Yeah,
all
just
preparing.
don't. Yeah, just don't overthink.
Yep.
Yeah.
Yeah, there's probably going to be some simpler problems where, you know, just kind of go with your gut type thing. I found personally that if I sit and overthink, like you're saying, I'll get more problems wrong. Where if I just go with my first answer that I thought of, it's usually right. And, you know, because that's your gut answer. And then you've been studying this stuff, so, you know, you got to trust yourself, right?
Yep.
Okay. So I know it's getting pretty late now. It's like 9:15. We've been doing this I started at 6. It's been a good long. Lots of stuff
Thank you for all
covered.
the help, man. I am probably gonna head out though. It's getting late.
Yeah, I was thinking the same thing. So I
See
don't
you
think I'm
guys
gonna be
tomorrow.
taking
and
the
Good luck.
exist tomorrow. I'll probably
Yeah.
take it
Yeah.
on Friday.
Good luck.
Good luck, everybody. And if you know, anybody wants more personal kind of questions or has anything they want answered, feel free to email. You know, I'll probably be up for a little bit yet here and in the morning. So don't be afraid.
Okay.
All right. Have a good night.